We're going to complete Module 1, our introductory module, with an overview of Six Sigma. We used this slide earlier to demonstrate the normal distribution, but what we want to point out here is that the plus and minus 3 standard deviations contains 99.73% of the population. That spread is real important when we start talking about the definition of Six Sigma. Also vital to the definition of Six Sigma is the understanding of process control and process capability. The top part, again, shows that a process is in control when it's stable, and the bottom part shows that process capability refers to the ability of the process to produce within the specification limits. We mentioned the Process Capability Index, CP, earlier. Here's the formula for it. It's the ratio of the tolerance zone, that's the upper spec limit minus the lower spec limit, to the statistic Six Sigma. And in this case, we're talking about 6 times the standard deviation. And so plus or minus 3 standard deviations is Six Sigma. And so this is a ratio of the tolerance zone to what 99.73% of the population would be. Now you'll notice that it doesn't matter where the process is centered. This is simply a ratio of the tolerance zone to Six Sigma. We're going to be developing the Process Capability Index, CPK. In order to do that, we have to start with the one-sided limits, CPU and CPL. CPU stands for CP upper, and it's the ratio of the upper spec limit minus the mean divided by 3 standard deviations, and CP lower is the ratio of the mean minus the lower spec limit divided by 3 sigma. So if we happen to have a one-sided limit that's on the upper end, we could use CPU as a process capability index. If we have just a lower limit, then we can use CP lower, but usually we have a tolerance zone with an upper and lower limit, so we can develop both CPU and CPL. Getting back to CP for a moment, it was a ratio of the tolerance zone to the Six Sigma spread, and so it was potentially what your process capability would be if the process was located in the center of the tolerance zone, but it may not be located there. CPK, on the other hand, does relate to where the process is actually centered relative to the spec limits. So it is the minimum of either CPU or CPL. So it tells you how your process capability is based on where it's actually located. So let's talk a little bit more about the centering of a process. Again, CP just tells you what the potential would be if the process was centered. The larger the standard deviation, the smaller CP. The smaller the standard deviation, the larger CP becomes. So CP is really just telling you the relative spread of the process. CPK, although it does tell you how you're doing compared to the limits, it doesn't tell you how you're doing relative to the target value. However, CP and CPK used together are very useful in creating understanding about what the distribution of the process variation is. Finally, a CPK value of 2 or more is what we consider to be Six Sigma quality, and we're going to illustrate that in depth on the next few slides. Here we have an illustration with several different distributions. Let's work through these to show what Six Sigma quality is and how CP and CPK interrelate. The top distribution, A, we have a process with a standard deviation of 2, and because the spread is large, we have plus and minus 6 sigma on either side of the process mean. That is, the mean is at least 6 standard deviations from the upper spec limit and the lower spec limit. And since it's centered we end up with a CP of 2 and a CPK of 2. So when the process is centered, CP and CPK are equal. Now if we look at distribution B, we see that the mean is shifting a little bit to the right. The standard deviation is still 2. So CP continues to be 2 because the location doesn't affect it. But as we get closer to the upper spec limit, CP upper starts to drop and it becomes 1.5. And since CPK is the minimum of CP upper and CP lower, it becomes 1.5. Let's look at C, and again our process has shifted a little bit, but now it's 3 standard deviations away from the upper spec limit. Again, CP is 2, but CPK has dropped to 1. So if you didn't have a look at this distribution, but you were told that CP was 2 and CPK was 1, you would know exactly what the distribution looks like, except for you wouldn't know if it's skewed to the left or skewed to the right, but you could visualize that it is off center. Next, in part D, we have a CPK of 0. That's what happens when the process is centered right on one of the spec limits. But again, CP is 2. So by now you're beginning to realize that CP all by itself doesn't give you the whole picture. But CP and CPK together do give you a pretty good picture of what's going on. And finally, if your distribution happens to be located outside of the spec limits, you'll get a negative CPK, but you'll still get a positive CP. So anyway, this is our first illustration of CP, CPK, and how they relate in a Six Sigma situation. Let's continue on talking about CP and CPK and process capability. In the first part here, part A, at the top, we see the same situation we started with on the previous slide. We see the Six Sigma capability identified, and we have a process that is very capable. We'll talk more specifically about Six Sigma and its capability on a future slide. Part B, we see again the process is shifted over, and so we need corrective action, but the kind of corrective action we need is to recenter the process. Our variation is in pretty good shape, but our centering is what seems to be the major trouble. So if we're trying to improve this process, we have to recenter the process. At this point, let me point out that in the world of quality improvement, it is typically pretty easy to recenter the process compared to reducing the variation. Part C, we see a process that has a lot more spread to it, and in this case we have plus or minus 3 standard deviations, covers the entire tolerance zone. So when that happens, we have a CPK of 1 and a CP of 1. Now in this type of a situation, you can see that it's really critical that we keep the process centered in the middle of the tolerance zone if we don't want to produce parts that are outside of specifications. The tool or technique that's used very often for this is statistical process control to monitor the process center. Let's look at D now. We see a process where the spread goes beyond the upper and lower spec limits. When that happens, we now begin to get CP and CPK values that are less than 1. So any CP or CPK value that's less than 1 is considered not capable. Finally, in part E, we have a process that, if it were centered, would be capable with a CP value of 1.33. But because it's shifted to the right, and we have too much of that tail sticking outside of the tolerance zone, we happen to have a CPK value that's less than 1. So when we see a CP that's capable but a CPK that's not, we know that again centering is the issue. Now it used to be when we first started using CP and CPK that a CPK value of 1.33 was considered a process that was capable. But as quality's improved, you'll find today that a CPK value of 1.66 is more of what's acceptable. And of course, CPK of 2 is what we call Six Sigma quality. I mentioned a few slides ago that when you're trying to improve capability, reducing the variation is the tough part. Typically, you can recenter a lot easier than you can reduce variation. This slide is intended to illustrate what kinds of tools and techniques can be used to reduce variation. Now, there could probably be disagreement among experts on this particular slide, but I think for purposes of illustration, it does serve us well. The reducing variation can begin with improving your inspection, and that's what acceptance sampling is attempting to do, is to use some scientific methods to reduce defects by screening out poor quality. Statistical process control also reduces variation a little bit, and so that can be used, but it's not going to achieve huge improvements in reducing variation. TQM or total quality control methods, again, you'll find some sources of variation and be able to reduce them using the tools of TQM, but it won't be that dramatic. Next, it shows on this slide Six Sigma methodologies, design of experiments, Taguchi methods. Those begin to really make inroads into understanding what your major sources of variation are and give you the ability to control some of your settings and make some decisions about parameter design that can make significant reductions in the amount of variation. And finally, this shows that you'll get some additional reductions by idiot proofing and doing some other things to try and reduce other sources of variation. The biggest way to reduce variation, though, is to put in a whole new system that has built-in reduction in variation. Sometimes you're able to achieve Six Sigma quality by just changing the system you have, modifying, and getting rid of sources of variation that are low-hanging fruit. Sometimes you don't have that luxury and you have to change the process or the system. So finally we get to the slide at the end of Module 1 where we explain in detail where Six Sigma came from. Where did this moniker come from that we've heard so much about? The top part of the illustration shows a process that has a spread of plus or minus 4 sigma between the upper and lower spec limits. If this process were to shift due to some assignable cause, plus or minus 1 standard deviation to the right or the left, then you would be producing defects on either side. It could be scrap or reworks, but these would be defective units. If, however, we have a process like shown below, where we've reduced the variation to where we have Six Sigma capability, that is, we have plus and minus 6 standard deviations between where the process is centered and the upper and lower spec limits, then if the process were to shift due to an assignable cause as much as plus or minus 1.5 standard deviations, we would still only have, as far as defects, 3.4 parts per million. Now 3.4 defects per million pieces isn't very much. This is almost perfect quality. Now think about this for a moment. If you have a process that has this small amount of variation, so that even if it does have some issues, it's still only producing 3.4 parts per million. Begin to think about the kind of quality you would have. First of all, you could probably eliminate inspection and eliminate inspectors. You would have parts assembling together that would work almost every time. The amount of defects that you would have and the amount of quality problems that you would have would practically be eliminated, and you wouldn't need to do very much inspection at all, so you'd save money there. This was what Motorola was trying to achieve, and that's why Six Sigma is such a nice concept, such a nice goal. And so the question is, can you do it? And anyway, that's what this is all about. I didn't think it was appropriate to finish this module in this part by just explaining what the definition of Six Sigma was without talking a little bit about the process. Six Sigma is a process where we use tools and teams and experts to work together to try and reduce variation. Here we have an example of one of the tools. It's called a cause and effect diagram, sometimes also called a fishbone diagram for obvious reasons, also called an Ishikawa chart. A fishbone diagram could be used by a team to take a particular defect and try to isolate what its potential causes are, maybe do a little root cause analysis, maybe do some designed experiments, but ultimately your goal would be to reduce or eliminate that defect and get closer and closer to Six Sigma quality. So what Six Sigma is all about is a program and a culture and a philosophy that, if done properly, will help you achieve improved quality.